Hi and good morning. My name is Jonathan Bailey and I'm the editor of the IHEAM monthly magazine Health Estate Journal. In today's webinar, which is being held in association with HEJ, Jeff Halliday, business consultant at WB Power Services, will discuss the impact of legislative and design changes and the drive towards net zero on the standby power generation market. He'll focus on how product standards and installation guidelines are regularly reviewed but don't necessarily keep up with the speed of change, and will also cover the impact of these changes on compliance with HTMO6 and, as he puts it, how newer and cleaner engines are changing the standby generator landscape set in the context of common specification clarifications. Jeff's career began as an apprentice working for Square D, later part of Schneider, before he moved into the critical power sector, where he's now worked for over 40 years. He is split this time equally between the UPS and standby diesel generation sectors, in roles ranging from customer service engineer, project manager, technical director and sales director to MD. If you have any queries as the webinar progresses, please type them into the panel on the right of the screen, and at the end of the presentation, Jeff will answer as many questions as time allows. I'm sure you'll find this an informative and valuable session. Over to you, Jeff.
Business consultant at WB Power Services Limited. A little about myself to begin with. I've over 40 years experience in the critical power sector, 25 years in the UPS element, with over 18 years experience now in the diesel generation sector. My experience is wide-ranging, covering many different market sectors, one of which is the healthcare sector. WB Power Services Limited is part of the Wilmot Group of companies. It's a private, family-owned company which has now been in business for over 40 years. WB is the UK's largest independent provider of critical power solutions, offering full modular and turnkey critical power solutions, standby power generator solutions including temporary power solutions as well, battery energy storage, CHP or combined heat and power. We have a full in-house mechanical and electrical design team. We have a UK-wide 24/7 service support, customised maintenance contracts with that, as I say, that full 24/7 call-out service. And we are Europe's largest Kohler Railco dealer. Legislative changes and the need to reduce emissions are driving innovations in all areas of our lives, with regulation, guidance and most importantly standards struggling to keep up with the change. Those technological developments in turn should lead to change and need to lead to changes in the way that we do things. But in the marketplace, the guidance we're given and the standards to which products are manufactured take time to catch up. This lag can be a good thing, as it gives manufacturers time to catch up with the development of their products, but the downside is that you end up with a significant variation in the quality and performance of what seems to be very similar products. So our seminar today considers the impact that these changes are having on product development and the potential impact on HTMO6. HTMO6 being the guidance given to the healthcare sector for the installation of electrical services. We have just a few minutes today, so I'll only touch on a few of these areas where these changes have an impact. So we'll focus today. Initially, I'll set the scene and the background to this seminar, how newer and cleaner engines are changing the standby generator landscape, set in the context of the rating and sizing of the generating sets, the effect on first step load acceptance, and the various types of load used in the modern healthcare sector. We'll then look at emissions in general and the legislation linked around with those emissions and the devices such as catalytic converters, diesel particulate filters that we can use to reduce those emissions. Look at resetting the dial and how we can reset the dial on testing generating sets in general, and the need and the urgency to align the HTMs directly with the ISO standard to which generating sets are manufactured. As you can well imagine, it's very costly to develop a new reciprocating engine from scratch, particularly one that isn't going to be produced in large volumes, unlike, for example, truck engines, which are typically power generating sets below 800 kVA. So many of the engines used to power generating sets over 1000 kVA, as I say, are produced in much lower volumes. But the build of some of these engines, though, are based around designs, some of which date back as far as the 80s or the 90s. Of course, they've been developed over time to enable the use of modern-day production and manufacturing techniques, and to ensure that they stay in line with emissions requirements. But their performance doesn't necessarily match engines of a newer, more modern design. So these newer engines have been designed from the ground up to ensure that they meet current and future emissions requirements as they're known today. They're built using technical innovations, new materials and new processes. This new generation of generating set engines have typically been designed and put into manufacture over the last 10 years or so. They've been built to achieve a much higher power density, with the focus of this action being to reduce fuel consumption and the consequent CO2 emissions, but also to reduce lower levels of other emissions, such as NOx, nitrous oxide, and particulate matter. This has been achieved in a number of ways, such as by the use of new lightweight materials and lower friction materials, with components being manufactured to much tighter tolerances than they were many years ago. This higher power output per litre of capacity, as we know in the business higher power to weight ratio, also offers the option of a reduced footprint, but brings with it a consequential lower levels of inertia, which are essential to the operation of the generating set. So we also add to that a better understanding of control and management of how the fuel burns in the cylinder, higher compression ratios, improved turbocharger technology, advanced fuel injection and control systems, many new innovations. But some of these innovations, which are focused on the reduction of the consumption of fuel and the emission of CO2, for example, come with compromises. So there is a cost. So, for example, this higher power to weight ratio, or per swept volume, means that there's a less rotating mass in the generating set itself, so there's less inertia. So how does this impact performance in relation to HTM06? For those of you that may not be aware, HTM06 is a document which provides the healthcare sector with guidance on the design and installation of electrical services across the entire healthcare estate. Diesel generators, on the other hand, are designed to BS-EN ISO 8528. This is the standard to which reciprocating internal combustion engine-driven alternating current generating sets are designed and manufactured. Over recent years, national and international regulations have driven engine development. We see this in motor vehicles, road-going trucks, as well as other uses of internal combustion engines, which includes standby generating sets. When it comes to how a diesel generating set should be operationally rated, HTM06 clearly identifies the need for it to be a prime rated generating set. The guidance here then is very clear, but that isn't true in all aspects of HTM06. To begin this quick review, we'll consider generating set first step load acceptance. This is an important consideration when it comes to selecting a new generating set. Here we see something of a mismatch between the ISO standard 8528 and the guidance given in HTM06. As we know, a generated set is a combination of an engine, alternator, control system, bed frame, etc. In ISO 8528, it is important to note that there are no specific requirements set out for first step load acceptance. The standard acknowledges that there is a difference in engine performance, and so it makes it dependent on the brake mean effective pressure that the engine is able to deliver. If you like, the amount of torque the engine can deliver into the shaft and hence make available to the alternator. The HTM guidance considers the engine standard, which is BS ISO 3046, which is at front and center when it comes to load acceptance, setting out the various performance categories as the set in the engine standard and not the generating standard, as we can see shown on the slide. In section 9.75 of HDM06, it states the advantages of higher load acceptance factors should be reconciled with the increased cost of larger generating sets. Generators that can satisfy the Category 2 of Class A specification of ISO 3046 series may be more economical and appropriate for most healthcare premises. So why? Let's take a quick look at some more comparisons to better understand some of the mismatches and their potential impact. So on this slide, we begin by looking at load acceptance of a diesel generating set, which is based on the ISO standard section 5. Here, the standard defines the load acceptance level on the basis of the brake mean effective pressure of the engine, not a specific percentage, which is what is required within the HDM. This allows for variations between engines and manufacturers in the ISO standard. Also in the ISO standard, performance isn't aligned with HDM06. Although 60% load acceptance at first step of a prime rated generating set is typically accepted as an industry norm. In BSEN ISO 8528, we have set out 4 levels of governing performance for transient conditions, i.e. this is the level of voltage and frequency deviations levels that are acceptable and the stated recovery time. In HDM06, in particular 16.8, in the validation and commissioning section, generator terminal voltage should not vary by more than 15% following a step load increase from no load to 60% load and then return to within 3% of the rated voltage within 0.5 seconds. As you can see, there is no direct link in this area between HDM06 and ISO 8528, with its recognition of different levels of performance between engine manufacturers or to the 4 governing categories set out in the ISO standard. Why is this the case when this is one of the most critical aspects of performance? We find some level of alignment between the two when we look at Category 3, but a recovery time of 5 seconds as per G2 level of performance. So slightly longer than the engine standard, but still achievable. So the HDM almost by default effectively sets the bar at 60% G2. This can be achieved in most cases with many sets, but certainly not all, and more so with some of the newer designs. So why 60% and why such a short recovery period? I've entitled this slide using a different approach. So we need to be more open to challenge the 60% load acceptance norm in this new environment. We need to think differently about the first step load acceptance. So why does it need to be 60%? Modern generators respond much more quickly to smaller incremental increases in load. What of our load do we consider to be the first step? With much battery-backed equipment, which is prevalent throughout the healthcare setting, being one factor which will preclude it from being a first step load. Some larger loads, such as cooling plant, take time to come back online and can be sequenced. Modern equipment can operate with a much wider range of voltage and frequency tolerances, for example. Using the tools we have, such as BMS, EMS systems or energy management systems, we can manage those loads onto the system. If you stay with the 60% first step load acceptance figure, you could be buying a larger set than you need. In that decision, you embed more carbon into the production of the product. Lifetime emissions will be higher, as will ongoing running and maintenance costs. I mentioned earlier about compromises. These compromises often come with gains made in engine efficiency and associated emissions reductions. These gains mostly come from improvements in engine performance, getting more power from the engine. Smaller engine capacity for a given power output is then linked with smaller rotating mass, hence lower inertia, and this can have a direct impact on the dynamic performance of the set, particularly on first step load acceptance. So there is a new balance that needs to be struck here. We need to weigh the benefits of lower fuel consumption in emissions versus the potential reduction in dynamic performance. In today's healthcare setting, there's an amazing and diverse range of electrical and electronic equipment: cooling plant, core electrical plant, lighting loads, scanning equipment, central IT equipment, a huge variety of equipment used at ward level. What of this equipment, though, and for example, particularly battery-backed equipment, actually presents itself as a first step load? So there is a real and urgent need to understand what the load of a hospital of today really looks like and how it responds under dynamic conditions. This is important so that we don't just carry on repeating what we've always done. This will become more urgent as we move to all electric hospitals in the future and will change the rules yet again. So we need to have a rethink. More on that shortly. Let's take a look at exhaust gas emissions. There is a plethora of emissions regulations and legislation, and a number of interested parties that can have an input into determining what is and what isn't required. Diesel generator exhaust gas emissions need to meet various regulations depending on the site, the size of the plant concerned, the sizing and rating of the application, and what already exists on the site. It can be a real minefield. So what I've put out on this slide are some of the regulations and guidance and people that are involved in this process. And you'll see there are national bodies such as the Environment Agency. We refer back as far as 1993 with the Clean Air Act. There's the Chimneys Act. More recently, though, the Medium Combustion Plant Directive, although this in theory doesn't have a direct impact on the healthcare sector, this is an important consideration. And then we have such things as the low emission zones specifically focused on London. An overview on generator exhaust gas emissions legislation and planning have changed significantly with new guidance, and so new guidance really does need to be issued. Elements of emissions reduction requirements in HTM06 in section 9.89 has been misleading consultants for a long time, as it prescribes the use of catalytic converters and particulate filters, the use of which depends on the engine, the age of the engine, the application, and what else is on site. So the guidance is very, very minimal here. The only potential requirements are to comply with the Medium Combustion Plant Directive and the Clean Air Act and building regulations. So let's look at the issue of emissions. Exhaust emissions, what are they? The area of emissions and emissions reduction is a very complex one. So what do we know? We know that air pollution in the UK causes an estimated 29,000 early deaths and has an annual health cost of over £15 billion a year. So I've listed on this particular slide some of the major principal pollutants that you can expect not only in a diesel generating set, but a diesel engine of any particular kind. So the ones that we know: CO2 has been a major drive to reduce this gas for many years now. But we also have to consider CO. Nitrous oxide is usually one of two, comes in one of two forms, either nitrous oxide or NO2, nitric oxide, both of which react with oxygen or ozone in the air to form nitrogen dioxide. One of the bigger issues, though, which has surfaced over the last 10 years is that of particulate matter. And we look at that in terms of PM10 and PM2.5. PM10 being particles of diameter of 10 microns and PM2 of diameter less than 2.5 microns, with the latter being the most dangerous. These can be produced directly in the engine or formed from reactions between the other pollutants in the exhaust system itself. Particulate matter is made up of a complex mixture of solid and liquid particles, including carbon, complex organic chemicals, sulfates, nitrates, you name it, it's there. The health effects of particulate matter are more significant than other air pollutants, though. Chronic exposure contributing to the risk of developing cardiovascular disease and lung cancers. Current evidence suggests that there is no safe limit for the exposure to these elements. With new engines, though, with newer engine designs, though, we're seeing a reduction in some of these key noxious elements. With engines running at higher temperatures, they achieve a much cleaner burn of the fuel, removing some of these elements at source. The job isn't finished, there's more to do, but most importantly, not all engines are the same. The engines must get hot enough in order to complete the combustion process within the cylinder itself. So what can we do about some of these emissions? There are a large range of different catalytic converters which can be used and deployed to treat the emissions coming from a diesel engine. We're clearly talking about a diesel generating set, but it does apply to diesel engines in general. So we can use diesel oxidation catalysts, or DOCs as they're known. These reduce carbon monoxide levels, hydrocarbon content, and some particulate matter. These are particulate filters, are the most popular, and they can capture up to 90%, 99% of all diesel particulate matter, which includes PM10 and PM2.5. CO can also be reduced by the use of a catalytic converter. So as I said earlier, the newer designs of engines have significantly reduced the amount of these elements discharged into the environment, but the performance will vary from engine to engine. So before you apply any of these after treatments, you need to check what your engine is actually delivering into the environment. To be clear, all engines sold in the UK will meet UK emissions requirements. Newer designs will achieve much higher levels than some of the older designs. So all of this you need to be validating through the tender process when you're procuring a new generating set. All of these devices that I mentioned can be fitted, but there needs to be clarity on what the objectives are that you're trying to achieve. So to what degree do you want to reduce CO? To what degree do you want to reduce PM10? You need to check what you need, but more specifically, the guidance stated in an updated HTM06 needs to be very clear on what these requirements are. It's important, though, to know that there is a limit to what can be added to the output of a generating set. Every element that you add adds back pressure to the engine, but one of the most important factors is that all these catalytic converters only function correctly when they are hot, and in order for them to get hot, the engine needs to be working at a high level of load. On this slide, we're looking at all or most of the different elements of legislation that are pertinent to the environment of the healthcare setting. So permitting via the Environment Agency, the Medium Combustion Plant Directive, and other EU legislation which is still pertinent in the UK setting. The generating set under the Medium Combustion Plant Directive applies to any generating set with a thermal input above 1 megawatt thermal. So that applies to generating sets between 300 and 400 kVA, so much less than maybe you would imagine. And these generating sets above that rating are required to meet a minimum or emit a minimum of 190 milligrams of NOx per cubic meter nominal. And this can be achieved by a selective catalytic reduction unit. But as I stated earlier, in order for these devices to work correctly, they need to be in an operating temperature band of between 250 and 400 degrees C. Standby generating sets must be at a minimum level of 40 or 50% load for this to happen. And it's important that a closed loop management system is also available on that to ensure that you're not introducing any unnecessary ammonia into the exhaust route. It's important to note that the combining of burning HVO fuel and the use of selective catalytic reduction offers the best solution for all new installations. Whilst we continue to use the internal combustion engine, it should be noted that we will always have issues with nitrous oxide emissions. I mentioned just a moment ago about HVO. The standard diesel that we use in our road vehicles is the same as we use in a standby diesel generating set, and it's a product which is manufactured to BSEN 590-B7. It's known commonly as white diesel and contains a 7% bioelement. So what is HVO? HVO is a hydrotreated vegetable oil and is manufactured to EN 15940. It's a paraffinic bio-based liquid fuel made from vegetable oils of many different kinds, such as rapeseed, sunflower seed, soybean and palm oil, for example. It offers an up to 90% reduction in the emissions of CO2. But in order to achieve that, it must be made from 100% recycled raw materials. If it's made from anything else, then the 90% reduction is really only achieved over the 30 years it takes to replace the plant products that it was made from. Is there more to it? Yes, there is. There's an increase of 2 to 3% in fuel consumption, but today most of the HVO fuel is not made from 100% renewable sources. It has a high palm oil content, and palm oil is associated by and large with deforestation. So the combination of burning HVO and the use of an SCR currently offers the best solution for reducing CO2 emissions. I've entitled this slide Generator Fuel Systems and Challenging the Norms. So in HTM06 section 9.8 there are a couple of statements here. So the first one is a day tank capacity should have no greater capacity than 750 litres or the equivalent of 10 hours full load, and it should be gravity fed. The main reserve tank or the bulk tank system is required to have a capacity of 200 hours at full load running for each standby generating set. The other statement, where the standby generators are decentralized, the fuel should be pumped from a centralized storage area. Okay, so we need to consider options to improve resilience, such as the use of a primary tank only eliminating the need for the transfer of fuel system, having a transfer system at all. So this often precludes the use of, for example, set-mounted base tanks because they don't have a large enough capacity to meet the 750 litre or 10-hour running time. It also precludes large belly or slab tanks, which is a common thing that gets used in a containerized solution. 9.87 of the standard also refers to dumping fuel where possible. But of course, dumping fuel is only possible if there is the availability for the dump source to be above that to which it's going. So gravity can be used for this use. We're now going to look at a couple of additional elements that could be easily added into HTM06, which would enhance the performance of generating sets. HTM06 9.8 only considers types of batteries that are used to start the generating sets, but they doesn't consider the quality and performance of those batteries, as they do differ from manufacturer to manufacturer. There are alternatives and better quality batteries that are available, and this would enhance starting reliability. There's no mention in the standard either of the number of cranks, i.e. the number of attempts that the engine has to start before it actually locks out and doesn't start. It doesn't look at the quality of the battery charging system either. On many larger generating sets, the option is available to have a dual battery, dual starter, and dual charging systems, and this would significantly enhance starting reliability and performance. Load testing a generating set in a healthcare setting, whilst mandated in HTM06, is often very difficult to achieve, and more so when it comes to a full system test. One option that is widely available, particularly on larger generating sets, and we see frequently taken up in the commercial sector, is the addition of a second breaker to the generating set. This provides the capability of having a local load bank connection. This enables the generating set to be load tested completely independent of any operational requirements of the healthcare setting. I mentioned earlier about challenging norms. In this element, I'm going to talk very briefly about generator maintenance and the impact that new engine developments can have on maintenance procedures. So these new engine designs, such as the Ralco KD series engine, offer lower emissions, higher efficiency, higher kilowatt output per swept cylinder volume, and a more compact footprint. Such engines run at slightly higher temperatures. Catalysts work at lower levels of generator load as a consequence. The potential to reduce regularity of testing, particularly on load testing or testing at lower load levels, all of which have an impact on the fuel used for testing purposes. So these long-held views that we have in terms of load testing and what that load testing format should look like can be challenged with these newer engine designs. Things are changing rapidly, so it's important to ensure that HTM guidance keeps up to date and reflects the current ISO BSEN standards, that installations comply with current legislation, and best products and practice are used to ensure that optimal reductions in harmful emissions of all types are achieved. During this time of transition and ahead of any major changes to the HTM, it's important to be open-minded and challenge received and perceived thinking on these important issues. I've called this one the changing workplace. So critical electrical equipment used widely throughout large hospital estates, including things such as IT infrastructure, scanning equipment, can be operated in a diverse range of locations throughout the estate. Critical procedures such as endoscopies undertaken in a range of locations within older buildings at any given hospital. Automated drug picking in pharmacies, for example, is now widespread. Standby generation is now required across the entire estate. Cost of energy continues to rise, as do pressures to reduce emissions. So what does the future look like? There is now a large focus or significant focus on reducing gas in generation plant, including CHP systems and boilers right across the healthcare estate. The focus on using more electricity. The removal of life-expired combined heat and power systems, for example, will have a significant impact on the amount of electricity required to fulfill that redundant function. So what does it mean for standby generators? With larger electrical loads, it will mean more on-site generation, more embedded carbon within the products that are being installed. What fuels will we use? Well, we've spoken briefly about HVO. We've spoken about gas, but gas doesn't necessarily mean natural gas. It could be hydrogen. It could be ammonia. That is a story of itself and not for today. What is the future for some of our existing systems, such as combined heat and power systems? Reductions in the use of gas-powered generation plant, including those CHP systems and boilers. We are led really to focus on our what we call Scope 1 emissions, and this is what I refer to as tailpipe emissions. So those are the emissions that we generate locally, such as the use of gas, the use of electricity. But we also need to consider our Scope 2 and Scope 3 emissions. The Ralco KD engines have full environment product declaration certificates. This is a measurement of life cycle of the product and all of those Scope 3 emissions, so the emissions that are embedded in the product at the point of production and typically used through the lifetime of the project. It's important, for example, that we don't throw away our CHP systems before the end of their useful life. We don't throw the baby out with the bathwater. We need to use an holistic energy approach. I've used this theme before, challenging the norms. The pace of product evolution continues, as do demands to meet emissions reduction targets. Product standards and guidance invariably will not keep pace with the legislation and product developments and improvements. We need to challenge those norms and the way things are done around here mentality. We need to embrace new ideas and new technologies. We need to fully evaluate technical options and take the plunge. It's the only way that we will achieve the level of progress and change that we need. And again, we don't throw the baby out with the bathwater. First of all, thank you for your time today in listening to this webinar. I've talked about just a few areas as time has been limited, and as you can understand, I think this is a vast subject, but we do as a business have a lot of resources available on our website. Things, for example, common diesel Gen HTM derogations, standby generation in the healthcare setting, greening standby generation. These are all white papers that are available on our website. Please do view the website. Can I also say that we run a number of CBD seminars covering a range of subjects linked with standby generation and provision of critical power systems. Thank you very much for listening.
Hi, thank you very much, Jeff. That was a very interesting and very comprehensive presentation. That was a very interesting presentation, Jeff, on a very topical subject, and there must be a lot of issues for standby generation and the use of it with the drive to net zero particularly, and issues such as looking at alternative fuels in the future. We have had one or two questions which I'll put to Jeff in a minute. I would encourage other members of the audience who are listening and viewing the webinar, if you do have any questions, as mentioned at the beginning, please type them into the box, the questions box on your screen, and I'll do my best to put them to Jeff, and if he's got time, which he should have, he'll answer them. He's also pointed out that there's a QR code at the end of the presentation which will take you to the WB Power website, and you will be able to contact him direct if you've got further queries or want to have a more in-depth discussion. Jeff, we'll move on to some of the questions if we may. One audience member has asked, what level of first step load acceptance can we expect to see with this new generation of engines?
As I tried to explain through the presentation, the ISO standard doesn't really mandate any level of load acceptance. So if I answer this by way of saying that if, for example, 1000 kVA generating set has a load acceptance, say, of 65%, we would probably use the same engine on a 1250 and a 1500. So kVA set. So as we progressively increase the load on that, so the overall dynamic performance or first step load acceptance of that particular rating does diminish. But to answer the question more directly, so typically we would be looking at somewhere between 50 and 60%. So normally, say in the mid 50s would be what we would accept. So not a massive reduction overall, but what we see is with consultant specifications particularly, they're always linked to a direct compliance with HTMO6. So if your genset can only deliver 55% and the mandate is 60%, then it closes the conversation on that particular product opportunity, and or the need to potentially need to oversize the set. So it needs to be a conversation, is the point.
Thank you. You talked in the presentation about some of the key technical innovations in the latest standby generation engines. What do you think have been the most significant recent technological developments in their manufacture?
I think the way the engine management systems have progressed over probably the last 10 years or so has made quite a significant and important improvements in the overall performance of the gensets. That's not also to forget the performance in the alternator as well. So over the period, more and more alternator manufacturers have been adding electronic and digital AVRs, for example, and these can manage much more effectively the regulation of output voltage output voltage is linked directly to the alternator, the frequency being linked to the speed of the engine. So both have a part to play, but it's that engine management system that's helped improve dynamic performance mostly as far as the engine is concerned, I think.
Thank you. A practical question. One of the viewers has asked whether the slides will be shared. The answer is yes, they will indeed be. They'll be sent out to all of the audience following the presentation. Somebody else has asked, when determining the flue location and height on a congested site, is modelling always required? If not, are there any rules of thumb to consider, except that it needs to be 4.5 meters above the highest building?
Yeah, that's a good rule of thumb, to be honest. I think what we find, not just in healthcare settings, but in general commercial installations, is that it's very much the decision of the local planning authority and their interpretation of the Chimneys Act, the Clean Air Act, and every other piece of legislation. So there's a lot of variation in that, but I mean, we still do install generators, for example, that discharge horizontally at ground level, but it really does depend on the actual location. I mean, in the healthcare setting, one of the most important things I think is to do some modelling to make sure that those flue gases are not going to get anywhere near air intakes into the building, particularly into the surgical areas. There's nothing worse than smelling diesel going into an operating theatre, for example. So modelling is key to that, I think.
Thanks for that answer. We've also had a question about whether there's a derating factor of using HVO compared to diesel.
No, there's no derating factor applied. They are principally the same. I kind of hesitate to say same calorific value. They work in a slightly different way as a fuel, but no, there's no need to derate the generating set at all.
Thank you. Another question, is there a white paper or guidance on fire protection systems taking a practical approach?
Fire systems in what context? Sorry, you're not going to be able to answer that question, I don't suppose, because of the way
the audience member has just said, is there a white paper or guidance on fire protection systems taking a practical approach? But it may be that they will elaborate, and if so, I'll come back to you on that.
Okay. We don't. The only white paper that we have on our website is relating to fire is a paper where we look at lock rotor current for the supply of standby pumps for sprinkler systems. That's the only white paper that comes to mind.
Thank you. Another question, are these newer types sets more prone to problems where high harmonics are present on the site?
No, not at all. If you think of the generating set as two specific areas, one is the engine and the other is the alternator. If there are harmonics present, those are managed and are a function of the alternator performance rather than the engine performance. They, of course, directly affect the performance of the gen set as a whole. As long as the installations are well designed and the equipment is installed is in line with current EU standards, then the requirement for those products should mean that the harmonics that potentially they re-inject back into the source supply shouldn't exceed 5%. So the alternators should be well placed to be able to deal with that, but it is worth looking at the overall harmonics of the building, particularly if you've got large variable speed drives and things like that could have a cumulative impact on the building system as a load, but also if they represent a high element of load on the generating set itself. There are various different types of excitation which you can add to the alternator to help overcome harmonics, but fundamentally harmonics are a source of extra heat into the system. So those are the things that you need to watch, really.
Thank you. So steps that engineers will need to bear in mind.
Yes. Yeah.
We've also had a question. As a rule of thumb, what step loads can we provide at the start of projects?
Sorry, could you repeat the question?
Yeah, the audience member has asked, as a rule of thumb, what step loads can we provide at the start of projects?
We have some fairly advanced software for sizing generating sets. The key elements that we look for in terms of right sizing generating sets would be the larger loads, really, and the starting method for those loads. The starting method is key, really. You know, if you've got a lot of small direct online starts and then they can represent quite a big peak of load. But there's predominantly today there are those sort of soft starts and various things like that. But it's the larger loads that play a critical part. But as I said in the presentation, with the building management systems and energy management systems that we have in place today, those can be phased. A lot of the bigger loads can be phased onto the machine.
Thank you. Another question, do you have any additional guidance on the application of the MCPD to newly installed generators?
We do have a paper on our website which directly links to the Medium Combustion Plant Directive, and that gives some information on that. We also have a presentation on it as well. So if that particular individual would like to make contact with us directly or through you, we can provide that information. But I think fair to say that the Medium Combustion Plant Directive has specific allowances in relation to healthcare settings and not-for-profit organisations. But it also is only applicable if generating sets are typically running for more than 50 hours per year. So there are a number of caveats in it which preclude the healthcare sector. It must be considered, but you'll find in a majority of cases the MCP doesn't necessarily apply to the healthcare sector.
Thank you. A question about your real-world project experience. An audience member has asked, in projects you've delivered, how have various loads been managed onto the generating set? And can you give any examples?
Yeah, I think probably one of the most onerous environments that we work in is in water treatment. There are lots and lots of pumps, some quite big pumps, particularly on the bigger sort of very, very critical sewage treatment works, for example. And there are also the kind of emergency situations where multiple pumps are required when there are high flows of water coming from rain and rivers, and where we hear a lot in the press about in high levels of rainfall where sewage gets mixed in with the water running through rivers, etc. So there's a very, very high demand for that. So we look at with the contractor, we look through how those loads need to be operated and how we can manage those loads on individually. I mentioned in the presentation that these newer design generating sets, for example, actually respond very well to smaller incremental steps. So what I mean when I sort of say that is that so a genset will be up and ready to accept load, single genset, probably within about 7, 8, 9 seconds. HTM06 requires the set to be at full load within 15 seconds. So if we, for example, hit the generating set with a 60% first step load, it's going to take 5 seconds to recover. But if you hit it with, say, 20%, 20%, 20%, the recovery time between those blips, if you like, increases in load can be as short as a second. So you can actually increment them on. So in the real life application, that's exactly what we do in a water treatment works. So you can have multiple pumps on very, very, very quickly.
One of the other questions, did you have any particular learnings from the COVID-19 pandemic in terms of resilience, etc.?
To be fair, we had very, very few problems through the COVID pandemic. We were, as a business, we were still able to operate fully through that. One of the obstacles that we had, or difficulties that we had to manage through, was where generating sets were in relatively enclosed environments. So, for example, in a container, two-handed working was quite a challenge because it is a very, very confined space. And as you'll probably all recall, we were trying to keep 2 meters apart at one stage. So if you're working in a very closed environment, that was really quite difficult. I think that was our only challenge, to be fair.
Yeah, the practicalities of that sort of close working must have been very difficult. Back on the fuel side, an audience member's asked, we're using HVO in one of our generators, and a particular manufacturer told me to derate my generator by 5%.
Okay. I'm surprised at that. I think there is no logical reason that I'm aware of for that. That certainly wouldn't be anything that would apply to the products that we sell, and because I mean all of our products are now certified for HVO use. I can't speak for any other manufacturer from that point of view, but I would also say it depends on the age of the engine as well. Or I think it's probably for 2 years or more now. So all of our product range has been certified for the use with HVO, but it's always our recommendation that if you're using HVO on a pre-existing installation, then that should be reviewed by the engine manufacturer particularly. And I would suggest, as if it's an older engine, then that may well be the case, but I can't speak for that without knowing more details.
Sure. Another question, what are the recommendations for controlling high current loads when carrying out monthly on-load testing?
On the generating set, specifically, there are a number of different ways in which a load test can be undertaken. So I'm not clear on the way the specific question is structured. But the load testing is clearly an important part of ensuring the reliability of a generating set. Maybe the question is coming from the direction of load level. I think I mentioned in the presentation that there are minimum load levels that should be applied to a generating set during that period of load testing. And with older gen sets particularly, that should be at least in the region of 60+%. It's really critical to get the engine up to full operating temperature. Reason for that is that if the gen set is run periodically at low load levels or at no load, which is quite common across the healthcare sector actually, where the gen set is just run offline for maybe 20-30 minutes or so, you can get a build-up of unburnt fuel, effectively carbon, building up in the exhaust system. And also you can get a pull-through of lube oil into the combustion chamber itself, where the piston rings effectively don't expand to the full extent. So lube oil gets drawn into the cylinder and then gets burnt. So you get a heavier oil burning in the cylinder as well. And that load test ensures that those unburnt elements are burnt within the exhaust system and the engine itself. Hope that answered the question. I'm not sure.
Yeah, pretty comprehensive answer. You mentioned in the presentation about combined heat and power systems. and the risk of some of them being closed down prematurely in hospitals to reduce hospital emissions. Why do you feel, as a company, why would that be the wrong thing to do in some circumstances?
Okay, so this comes back to the scope 1, 2, and 3 emissions. So let me try and give a brief example. So if you are, I mean, we're in a period of transition. So what exists today may not exist in 10 years' time. So it's important to say that, as I can sound a bit like a heretic in terms of greenhouse gases and emissions and all that sort of stuff, and I'm certainly not that. So at times during the week, particularly winter times, we as a nation are quite dependent on gas as a source of power generation for the national grid. That gas is burnt at an efficiency probably somewhere at best in the high 30s. So we're looking at, say, 37, 38% efficient, for example. If you add grid losses onto that, you can drop that by at least 2%, maybe a bit more. And then you've got your own losses within the building and the estate itself. If you're running a CHP system, that CHP system is producing electricity locally, and it's also producing hot water or steam. Now, if you were to take away, so that CHP system runs at somewhere in excess of 60% efficient. So if the grid is burning gas and the electricity that you're using in the hospital is from the grid and not from your CHP system, then the gas that's being burnt is being burnt at much less efficient, in a much less efficient way. So those are the scope 3 losses. So if the aim of our energy efficiency drive in the healthcare setting is to reduce scope 1 emissions fundamentally, and to achieve that you can switch off your CHP system, but in doing so you actually increase your scope 3 losses. So you need to look carefully at the balance between those two things. Is the point that I was making.
Thanks, Jeff. You mentioned there being quite a significant number of legislative and guidance documents in place controlling generator and other building emissions. What after treatments should hospitals and healthcare facilities be using, and or do you see in your experience across the UK healthcare estate?
We see very little, to be honest. And that was kind of one of the points of raising this this kind of subject content, really. We do see a lot of trusts now putting in selective catalytic reduction in order to reduce NOx emissions. It does also catch a little bit of the particulate matter as well. We have done some installations with other catalytic converters and particulate filters, so we have done those. But I think the biggest issue, and the reason I raised it in this presentation, was to try and provoke thought, really. There's this very bland statement in HTMO6 which says you'll need to use a catalytic converter. Well, there are many versions of different types of catalytic converters to deal with different elements of the exhaust emissions. So we do see a range. As I say, SCR, selective catalytic reduction, is one, particulate filters are one, but not widely used across the estate in general. But I would say if you are going to add that into the list of requirements because it's a good thing to do, then you need to be clear on what you're trying to achieve, rather than just say I want a particulate filter or I want a selective catalytic a catalytic sorry, brain's gone freeze. To say to reduce carbon dioxide, for example. So what percentage do you want to try and reduce it by? So it's important to know the specifics.
Thank you. There's a lot of talk about alternative fuels. What fuels do you see potentially being used in the future to power standby generation requirements? And hydrogen's been talked about a lot. Do you think it's going to be a viable future prospect as things stand?
Do I think? I think it's got a long, long way to go. I think there are a number of issues in relation to using gases in standby generators. So diesel engines are the ignition process is by compression process, whereas gases, and I include petrol as that, is a spark ignition process. So they are two different processes. One of the problems that you get when you use gas as the fuel source is that the dynamic performance of the engine is much reduced. And the capacity of the engine needs to be much bigger because the calorific content of gases is much lower than diesel. So for example, if you were using natural gas, the equivalent hydrogen volume would be approximately 3 times the volume of gas. So if we were to feed the standby generators on a hospital in the future off of the gas network, which was hydrogen based, then the gas network would need to run at 3 times the pressure it currently does in order to get the same calorific value of gas through it. So it does bring a number of complications. And I think also people in the healthcare setting will be aware of how costly potentially it is to look after gases. So, you know, you've got oxygen is a prime gas that you use in the healthcare estate, so it needs to be kept cold. CO2 as well, I think. So hydrogen needs to be kept under pressure and it needs to be very cold. And there's a cost of keeping those gases to high pressures and cold. But it's also the volume of the gas that you need to keep if you're going to run your gen sets for 200 hours. It will be a colossal storage problem and very, very costly to do that. So I don't see hydrogen particularly as a silver bullet that's in the near future, certainly, that's going to solve that problem. So I think you could say I've got a vested interest to say this, but that's not the case. Is that diesel, I think, will be around for quite a long time yet in the standby sector.
Thank you very much. Well, that concludes the questions that we have. I'd like to thank Jeff Halliday very much for a very interesting and comprehensive presentation on a very in-depth engineering subject. I'd also like to thank all of our audience for attending today. As mentioned, copies of the presentation slides will be sent to all attendees, and it'll also be possible to get in touch with Jeff Halliday if you've got particular questions you want to ask. He's happy to take those. Don't forget there's a QR code on the last page of the presentation, which will take you to the relevant website. Thank you all for attending. I hope it's been informative and interesting. And thank you very much, Jeff. With that, the webinar concludes. Thank you.
You're most welcome. Thank you very much.